So today we're going to briefly review some of the examples of vectors and doing things this time by hand as opposed to through the PowerPoint. And I'm going to start on matrices, which are kind of the natural extension of these data sets that go from one dimension, so just like sort of an array, single array of numbers, to these multi-dimensional arrays. So without further, and then we were going to, just for a brief generalization and overview, we're going to go get back to the lecture in the PowerPoint. So you'll see that that's actually my lecturing style. I kind of go back and forth the PowerPoints, which are posted for you as material, and writing something that is typically done in the sketchbook online so that it's visible on there. And once we actually start programming, I will be programming in class in front of you. Or you will be doing some of it, and it will be walking around, and then I will execute it in front of you. And as such, you will see that I will also make mistakes in front of you, and that's the whole point. Okay? So you will see how you go, and you always watch for mistakes as you keep going, and you have to correct them. So there is one thing that is to be said. So these, now that we are writing in these problems that we actually do in writing, you're writing them, and then another human, that would be our TA, is actually looking for mistakes. So there might be some small mistakes that you do on the way, but you actually arrive at a correct result. And as he goes, he's looking, oh, is procedure there? Yes. Is the end result good? Yes. Moving on. Okay. So that's how grading essentially works. Now, if you made small mistakes, so basically any small mistakes can pass through a human grader. Now, as you do small mistakes in a computer, it's very intolerant of mistakes. Some of them actually can pass through, but it's going to misinterpret, and that's actually worse. It's best if it tells you immediately it doesn't understand things. So you miss a comma, problem. You miss a comma, there's no problem if a human reader is because we are quick on recognizing, oh, this is, you know what you're doing. Good, good, go. Right? Otherwise, we would grade for it. So that is one thing to understand as we are going to today work on problems, and there's going to be your first homework will be to do things by hand. But as we switch to a computer is less tolerant to small mistakes. And it's going to annoy you until you fix them. When it doesn't annoy you and you made a mistake, then it's actually real trouble because you don't know you have a mistake. And you're counting, but oh, things are going smoothly. Meanwhile, you're blowing up a bell somewhere. Oh, sure, okay? So you have to be attuned to that, okay? Computers and humans communicate differently. But for now, let's communicate as humans. So we said that we have vectors, and vectors are typically arrays. As we play with examples, we're going to play with small examples. So let's say that I have an example U. Oh, again, the same problem, didn't you? Remember these? Anybody has a glove, let me know. If not, I'm going to do it. So my software is not always operating smoothly. So this is a vector U, 3, 2. And I'm going to call this mathematically a 2 by 1 vector or a column vector. Okay? And I'm going to give myself another one, V, which is minus 2, 1. Okay? So these two are column vectors. Okay? 2 by 1, this is essentially understanding these vectors as, whoa, hi, and you can now see some other files I'm working on. So this is understanding a vector as a matrix. And we're going to get to matrices, but they're going to have more columns than just one. That's an idea. Let's see. Engineering solution 101. All right. So what I could do is transpose this vector. So there are some operations that I want to be fine on this vector. Thank you, that works. So if I transpose a vector and just flip it and make it a row vector, I'm going to have 3, 2. And that is a row vector. So this transpose operation basically flips columns to rows and rows to columns. Okay. Works until it doesn't. So transpose operation. So with that paper, I'm accessing something else. Just a moment. I'm going to engineer. The problem is that sometimes my computer, and I need to reboot for that, which I don't want to do that, is too sensitive to my touch, and I cannot easily fix it. I learned that last week until I actually changed my computer, but that's not too sensitive stuff. All right. Not going to count on it. So this is a transpose operation. And I can work both with vectors and matrices. I basically flip columns to rows and rows to columns. Now, one thing that we learned is that we can do linear combination of vectors that have the same dimensions. And this U and V do, so I can actually do that. So I can actually do something like this. My W, which is a new vector, is 2u minus 3v. So when I do 2u, and u is a vector, then I'm going to multiply every element that I have in that vector. And I could do that with a matrix as well, something larger. So every element I have in there, I'm just going to multiply by 2. And for v, every element I'm going to multiply by 3, create those two new vectors, and then do subtraction also element by element. So I just work with corresponding elements in this array. And since they're ordered, that should be no problem, right? So basically I have 2 times 3, 2 is 6 and 4, minus 3 times minus 2 is minus 6, and plus 3, apologies.
Oh, that's supposed to be 2u minus 3v. Is that what you said?
Yes, 2u, this is 2u, and this is 3v. So 6 minus minus 6 is 12, and 4 minus 3 is 1. So this is my new vector, which is a linear combination. Now, we last time introduced norms. Does anybody remember how norms work? So if I was actually looking at this in space, or in this case, two-dimensional space, I have my x1 and x2. You could refer to them as x and y, however you prefer. Okay. So for u, I had 3, so I go 3 in the first dimension, and then 2 in the other dimension. Okay? So this is essentially my vector u. And if I was working with Euclidean norm, so norm is some assessment in form of a single number of this vector, so that I can compare vectors. So one would be simple the length as we normally look at it. Okay? And the length of this vector would be labeled as a 2 norm. It's basically square root of 3 squared plus 2 squared. And that in this case is square root of 13. So that is Euclidean or 2 norm, also known L2 norm, either way. Okay? If I had bigger vector, of course we're always playing with these toy examples that are small but they're easy to conceptualize. If I had thousands of entries, I would just go and square each element add them all up and take a square root of it. Now we also had one norm, which is simply the same thing. It is actually absolute values here, so it's basically sum up basically this, right? And then I don't have a root, one root, it's nothing, right? So I just leave it as a sum. So one norm and two norm effectively as a formula kind of work the same. So I just add these values and that is 5. And one more norm I have that we're gonna use, it's infinity norm. It's simply the maximum between the two absolute values, or 1,000 absolute values if I had 1,000 of them. So this. So I can see that in these three cases, I'm gonna get slightly different numbers. That's fine. As long when I compare two vectors, I use the same norm to compare them. The rest is just like it's a little bit of a stretch scale. And different norms will bring up different things. So this max norm will kind of pick out the worst scenario, the largest number. So if this was actually 302, right? Then that 300 would kind of take all over. If you have a lot of error, measurement error, and you don't want to count outliers, that would be sort of an outlier, then you don't use this norm. So it depends on your application. And then we commented on the 1 and 2 norms that there are actually different types of distances. So 2 norm is a direct distance, except that I don't fly as much as I'd love to. Right? So I gotta walk around on a grid often, and if I walk around on a grid, I'm essentially doing a 1 distance, 1 norm distance, whereas if I was flying, I'm doing a 2. So if I'm an airplane, then 2 norm makes sense in a curved world, but okay, depending how far you fly. Because it's not necessarily a straight line, it's a curved line to South Africa somewhere, okay? But on a regular distances locally, Earth is flat. So locally we can actually just do straight distances. And in one norm, if I'm snapped to some sort of a grid and I'm restricted to where I can walk and move through, then I have to do one norm. So if you think about Google Maps, they're not working on a perfect grid, but they're working on a grid of streets. So they're essentially one of these constrained norms similar to norm 1, right? Because you can't fly. Okay, so this is our review of norms. Now let's introduce one more thing that we didn't mention last time. I actually just kind of started. What would be the angle between two vectors? Okay. So the angle, if I had u, so I drew u here. Let me draw v as well. So it's -2. Oops. Let me extend this coordinate system a little. So it's -2 in first direction, and then 1 in the second. So my v is right here. And essentially, I have an angle between them. And I'm going to call it theta. And there's actually a formula for it. So if theta is my angle between u and v, to use math notation, cosine theta is, I'm going to introduce in a moment a scalar product, u dot v, divided by norm u, 2 norm, and 2 norm for v. So it's kind of a normalized scalar product, where scalar product u dot v, in this case, since I have 2 dimensions, is simply my first dimension times first dimension for the both vectors plus u2 v2.
No, U1, V1.
Oh,
U1?
sorry.
Uh-huh.
No, it's not. It's a dot.
Yeah. It's a dot product, yes.
Sorry.
So this is my scalar product or dot product. And in most general case, it's simply for two vectors. I'm going to do a general formula here if I had more dimensions. My formula, U dot V, is sum. This is my sigma sum for all of the dimensions, if I had n of them, UIVI. So this is just a general way to write, even if I had thousands of it, this U1V1 plus U2V2 plus U3V3 plus, if I had 1,000 of them, I don't want to write them all down. So this is my symbol that allows me to do that. So this n could be 1,000 in that case. And again, we mentioned that vectors in petroleum engineering are the ones that are typically related to well logs. Okay, so there's these measurements that show up every foot, and 3,000 feet is a shallow well. Okay, they go way deeper. These days, 10,000 feet is not a problem at all, and it's common especially in unconventional resources. So sometimes wells start shallow but then go deeper, right, as you find more formations below to exploit.
Is that also in mud logging?
Hmm?
Is that also, I mean, we have well logging, do we also have mud logging? I know
Yes.
we have mud engineers and all of that.
Yes, so, well, basically you can always log the data as you're doing something. Okay?
Regardless of what it is, welling or mudding or...
Could be anything. So it could be drilling in itself, which is mud logs are typically drilling. So during the drilling process, you're circulating mud, which is basically water plus additives that make water heavier, and that serves two purposes. You have to have a density of your water enough to keep all of the fluids and stresses at bay. That's the function of whatever you're circulating in the water. Otherwise, it's going to go out. So to keep fluids at bay, you've got to counter them with the same level of pressure to counter the stress that you have from the mechanics of the situation. So that's one. And then the second one is you're drilling, so you're creating the material as you go. You're essentially grinding through the rock, very similar to what your dentist does. Right? And your dentist also circulates fluid. Sorry to remind you how dentist works, but they can circulate water because it's very little material to flow it up. And then they actually also have suction, which we don't have anymore. So that mud or these heavier pieces of rock, you have to have a heavy fluid to pick it up and take it out. Just water won't do it. So that's what's referred to as mud. And then as you're doing anything, like you're rotating the bit, you have rotations per minute. You can log that. At every time stamp, you also have whatever rotations per minute. That tells you how difficult the formation is to drill through. Because the more difficult rock, you will need more rotations per minute, and it's going to take you a little longer to drill through. That's a harder material. So that type of information is a log that tells you what are you encountering as you're going through, and it's very important to analyze, of course, because otherwise we don't know. Before that, at the beginning, we had that seismic, right? But seismic is sort of implicit. Like I knocked on the rock and I was hearing back, and it's not always straightforward to know what's under there. We analyze it, we have a guess. Yeah? It's an educated guess. And then you actually go and drill, and then you'll find out okay, in that location. And then once we drill through and create the hole, before we stabilize the hole, you basically cement around you and put casing so that you stabilize it. Otherwise, earth stresses would close it up. Then basically you have to go and do well logging, which is essentially knocking on the formation with all kinds of waves and anything else that you can spring on it to again find out what is the type of the rock that I have as I go down. So from analyzing literally two different materials, those two different materials have two different sets of mechanical properties. So all the Young modulus and whatever it is that you're working on in solids, you're going to hope to find out from knocking on the rock again and hearing back. And of course, we want to find out, hey, do we have fluids in there? So we could have this type of a different sound, both because rock is the same rock but with a different fluid inside, or a different rock, period, with fluid or no fluid inside. And I gotta find out. So we need multiple logs to figure that out. So one would be a resistivity log. Okay? I send some electrical current in there. Water is conductive, oil is not. No. So that's based on the feedback. I'm trying to figure out, do I have a conductive fluid or not? In combination with different sounds, hopefully I can figure out. So I'm actually comparing these two vectors, and you're going to get to a lot of comparison like that in your formation evaluation or well-logging course, whatever it's named, sorry. One of the two. So that's coming later on. That's typically class taught by Dr. Berger. Okay. So in that case, you're going to have all this graphical description of these vectors of resistivity, porosity, the P wave velocity, S wave velocity, which is essentially this called knocking and sending a wave through. And based on that, you kind of try to compare them and figure out what it is that you have. So that was a long story, too. But again, I want you to understand that we play with very simplistic vectors, but in reality, you need computers to help you analyze these things, especially when they have more than 3 or 4 or 5 elements. Okay? And that's why you need this class to learn that there are effective computing tools that can help you out with that. Okay? All right. Where? Dot product. All right. So let's actually compute the dot product of this thing here. U1 V1 is, I'm going to continue in the same color. So 3 times minus 2 minus 6 plus 2 divided by, we already did, this is square root of 13. What is V? Square root of 5. Thank you. So this is going to be minus 4 divided by square root of 65. If I calculate it, it's roughly 120 degrees, which I can actually see from the picture. If somebody has a phone.
119.74.
There we go.
Our cosine of -4 over root 13 times root 5 is 119.74 degrees.
Thank you. So if you don't have a calculator, install one on your phone. You can install, the basic one is already there. And the scientific one, you can go and find an app that is a scientific calculator, by the way. Okay. You can actually install Python on your phone too, but we're going to get to that. All right. Let's now get to matrices and get this a little. So this was give or take a review. So what are now matrices? Let's actually play with the simplest of them examples, small one. So this is going to be matrices. They're essentially higher dimensional array. So the location is important in 2 dimensions. So this is A is 1, 3, minus 2, 4. If I was on the screen, this screen right now is about 1400 by 900 on my computer. I'm not sure what it is on the projector, but the resolution of the projector is a little less, so it's something smaller. So that is a matrix, and at each point here, I have 3 values, which are red, green, and blue value that give me the color. If it was with no color, then it would be just like 1 value, and that's my grayscale. Okay? So these images, any image that you have on your screen, on your phone, on your video stream, whatever it is also a 2-dimensional array. It's a matrix. And then your video has a picture at every time point, not every time point, but they're fast enough for your eyes not to realize that there's a gap in between. Okay? So if I go quickly through matrices, you're going to get this movie. Okay? So that means that like how many frames per second is basically the movie speed. So if you put 5 frames per second, we're typically fine. We can't figure out that there's a gap in between. Okay? So that is actually then a stack of 2-dimensional array, and that would be a 3-dimensional array. So it would have basically your x and y of the screen and time, or time point. Okay? So that would be a 3-dimensional array. You can keep going. It's just very hard to visualize as you keep going. 3 dimensions we easily visualize, but 4, 5, 6, 7 dimensions and so forth are harder to visualize, but they do exist, and math can deal with them. So we're going to mostly work with these 2-dimensional array matrices, and in 1 or 2 occasions with 3-dimensional ones. But just do understand that you can keep going as long as you have computational power to do so. So this is a 2-dimensional matrix. It has basically, we're going to call it 2 by 2 because it's 2 rows by 2 columns. So essentially, when I look at the matrix, mathematically, I can look at it, oh, well, this is 2 columns. First column is 1 minus 2. Second column is 3, 4. Or I can look at it as 2 rows. First row is 1, 3. Second row is minus 2, 4. How do I decide to represent my data is all great. It's up to me as long as I don't make mistakes, right? So if at one time I count rows and columns and then I come next day and I flip them, I'm going to make mistakes. So I have to be consistent in whatever it is that I do. So, bless you. And so this is my 2-dimensional array. And that is what we call a dimension of A. So dimension is 2 by 2. 2 by 2 is dimension. Now, one of the most important thing in basically representing a whole lot of problems that we deal with, especially with data, is multiplication of a matrix and a vector. And what that does is a generalization of my function. If I had a function, basically my function f of x for a scalar, f of x is 3x, that function takes one number and sends it to another that is 3 times the original one. Okay? Now, what if I want to send a vector to another vector? Then I actually have to have a matrix or a 2-dimensional array of coefficients. It's not just 1, 3, but it's multiple of them that will give me the vector that I need. Okay? So if I had a vector, so generalize, generalize. I need matrices. So basically, if I have a vector u, I can send it to a u. So this is a vector, and this is going to be a vector. So if I want to map a vector to another vector, the simplest way to do it is to use a matrix of coefficients. Okay? So if I wanted to stretch a vector, for instance, my vector is, what was it, -2 or 3, 2?
3, 2.
and I had 2u, right? This is actually the same as 2, 0, 0, 2, 3, 2. So simple stretching I can do with a scalar if I want the same scalar in both dimensions. But if I wanted to stretch the first dimension by 2 and the second one by 3, for whatever application I had, then I would actually have to, so basically my 2, 0, 0, 3 times 3, 2 would give me 6 here and 6 here, so that my first dimension would get stretched by 2 and the second one by 3. And for that I need a matrix. I cannot do it with one single scalar because I'm not doing the same thing in every dimension. So the moment I want to do something more complicated than just stretching everything the same way, I have to use matrices. So here we are actually going to motivate now multiplication. So how do I multiply a matrix and a scalar? So more generally, let's say that I have really my A that I had here, U, which is 1, 3, minus 2, 4. So the operation that is defined as a multiplication. So first thing, I'm going to take my U vector, which was 3, 2. And I'm going to do the following. I'm going to go, essentially, and I'm going to say, take the first row, interpret it as a one-dimensional vector, and do a scalar product with this column vector U here. So this is essentially 1 times 3 plus 3 times 2. Do we agree that that is a scalar product between this column, row vector and a column vector? So that's going to be in my position, this first position here. And in the second position, I'm going to take my second row and also multiply it with this column vector and do a dot product. So that's going to be minus 2 times 3 plus 4 times 2. So what is the result? 3 plus 6, it's
9, 2.
9 and 2. Whoa, hi. And that is essentially my vector result. So we're going to, this is just a very small example, 2 by 2 matrix times 2 by 1 vector. We're going to generalize this to a more general case next time. So I see you on Friday. And again, this video will appear sometime soon.